Okay, so if we go to the syllabus and today is right over here, lecture 2 exam, exam 2 will be posted later today. And then tomorrow's lecture, I'm just going to post this on, I'm going to do it at 4:30. If I'm going to be, there's a possibility I may be late for that. If I'm going to be late, I'll let people know. But what this is just kind of an overview lecture of some topics for the final lecture in the course. And I just want people to view it. And then the assignment will be a survey to select what do you want to hear about. So it'll be reactors, nuclear forensics, the nuclear fuel cycle, application of isotopes, and technetium chemistry. Right, so today, let's see, the nuclear reactions quiz is due today. So this is just the lecture on nuclear reactions. Let's look at the lecture quiz. The lecture quiz goes over, it's based upon something from the literature, an article on rutherfordium excitation functions, and you can download the article and look at this. So this will have some details. So answer the questions. And this is figure 1 from this work. It's actually figure 7 in the document. So the reaction to form rutherfordium from curium, it uses curium as a target. Select the correct projectile to form a rutherfordium isotope. Well, let's see. If we go to the article, oh, let me see if I didn't download the article. This way we can open it up in a new tab. Well, the title of the article gives you what the other, what's used to make the rutherfordium isotope. Curium-248 and this isotope of oxygen. So you can select that from here. From the laboratory data, which is the excitation function. Let's look at this. Now so what would be the optimal particle energy on target? So this is in the laboratory data. So just tell me where the peak is. You got to select that data point. You write it in, it's an MEV. And what's the cross section at an optimum particle energy? Well, if you go over here and you do the intersect here, you get the cross section. It's log, so that makes it difficult. And then as another difficulty or some complicating factor could be that I believe the cross section is listed in here. Someone had answered it by reading the article, and spontaneous fission events. The half-lives were evaluated. No, that's the half-lives of the excitation function. But this is Babak Kadkodian, was a colleague of mine in graduate school. He did work on gas phase studies of rutherfordium. And assuming the production cross-section of this beam energy is this. So there's some values that are put in here, and then there's a bunch of cross-sections that are listed here. And this is kind of like a value that people have looked at. That's quite honestly, that's not what I was really thinking of here. I was trying to get, kind of want people to answer where this would be the intersect, but I've expanded the range of the answer to include what's in the literature. So I've changed it a little bit based upon what some people wrote in the blog. And then, okay, if I look at this, as the energy increases, it goes up and then it reaches a maximum that the cross section starts going down. So why does this cross section decrease as the energy reaches this maximum, right? So as I get more energy into the system, the cross section for this specific reaction, which if we remember is, what do I have it here? Yeah, this is for Rutherfordium 261. So this is a 5N reaction. So why does it go down if the energy increases? And it has to do with the fact that I think the figure over here might have it. Yeah, this is, no, it doesn't say specifically that's the 5N reaction. But as you increase the energy and you add more energy to the nucleus, the nucleus is at a higher excited state. And it can de-excite through different means. And one of the ways really excited nuclei like this de-excite is by evaporating off neutrons. So as you increase the energy, that peak is at the 5N. If we have more energy, you're likely to start, some of that compound nucleus de-excites by evaporating 6 neutrons. So it's no longer Rutherfordium 261 to be Rutherfordium 260. Mm-hmm. So let's go through the lecture, and I'll just hit the highlights of the nuclear reaction lecture. Are there anything else you think we need to cover, or are we good with just this lecture?
Yeah, no, I think that makes sense.
Yeah, me too. I mean, everyone seems to be doing fine in terms of what they're doing in the course. So, all right. So let me just hit the highlights here. This is, in essence, this is our full system. We've got a target. Oh, we've got a projectile. I need to do this. I probably need to say on the slideshow, don't do that. Okay. All right. So this is the kind of the full system: target, projectile that makes some dinuclear system. And then a lot of things can happen. It can just kind of almost break apart again. It can make this compound nucleus. This compound nucleus can break apart again, or it can make this fusion product and this de-excites, and then you have a new nucleus. So what I really want to make sure that we get across, one is the notation. We've been using the notation for the entire quarter so far on nuclear reactions. I just want to formalize it. I'm going to talk about a little bit of the types of reactions, and then I guess talk about some of the types of reactions, why cross sections can change so much, and then have discuss some of the details of some of the other reactions, and then really go into nucleosynthesis, because nucleosynthesis is how all these reactions can be applied for understanding how elements are made in stellar processes, which I think as a chemist, one should, it's kind of cool to know where all the elements come from. All right. So some of this stuff, we talked about the energy before, the Q value, but this is the shorthand, and we've been using it in the course, but now we're going to formalize it for understanding how to display a nuclear reaction. So this is nitrogen 14 plus helium going to oxygen, 17 plus a proton, and then the Q value energy. The way we can write this is that the target is listed here, the projectile is listed here, one of the products that come out, usually the lighter of the products, is listed here, and the other product nucleus is listed here. So it's pretty straightforward, and we've been using it already this quarter. I do want to point out that there is, the energetics of this system is per atom, and if you convert it to per mole basis, you get pretty large values. Usually we measure chemical reactions on terms of kilojoules per mole, and this is more like gigajoules per mole. So that's where the energetics come from, and it's because you're talking about mass changes, small mass changes within the nucleus. Okay, so Q values, we've already talked about Q values, and we're going to talk a little bit more detail about the Q value, and that is the kinetic energy of the particle is equal to the projectile divided by the projectile plus the target times the Q value. So let's say I have a reaction that I'm interested. What's the kinetic energy of this reaction? And if I'm going to, I know the Q value, I can look up the Q value for this reaction. And I can say, well, I'm going to need to know something about the energy of the projectile and that's used in this reaction, and it's equal to the energy T, the kinetic energy, that projectile is equal to projectile plus the sum of the projectile plus the target times the Q value. So if I have curium-248 and oxygen-18, the projectile, if it's curium-248, I get this value. If the projectile is oxygen-18, I get this value. So if I'm going to look at this nuclear reaction, and if I'm going to use a heavier projectile, that means I'm going to have a lot more energy into the system. You don't want to do that. You'd much rather have a lighter projectile. This is a fraction of the Q value, where here it's almost the entire Q value, which means that nucleus is going to be excited. If I were to use the curium-248 as a projectile, that nucleus is going to be very excited. It would be it also must make less sense from the accelerator point of view to use the curium-248 as a projectile, but this is some of the physics behind it. And then this might have been something that you've seen in other classes, and it has to do with when we talk about doing these energetic calculations, what are we really talking about? There's two types of ways of looking at a reaction. This is the laboratory frame, where I've got a target here and I hit it with a projectile. Then afterwards, things are moving, right? So this is also moving a little bit, but let's say it's stationary. This projectile hits into it. One product goes one way, summation product goes another way. The way that we really do the math is based upon center of mass, where the reaction happens in a center of mass. We basically say that both particles are moving and the reaction takes place in the center of mass between the two particles. There's a relationship between the laboratory frame and the center of mass frame with the mass of the particles and the mass of the targets. So if I know the center of mass calculation and I want to find the laboratory calculation, I can relate that based upon the masses of the projectiles and the masses of the targets. So laboratory frame minus the center of mass frame is equal to the total kinetic energy dissipated in the reaction. Because here, the particles don't take away any of the kinetic energy. Here, this is, has no kinetic energy and after the reaction, it has some. So you're trying to compensate for that. And we need to know that because if I perform a calculation, I need to know how that calculation is useful for me to be able to perform the study in the laboratory. So this we relate to a threshold energy, right? It's a threshold reaction, and it's at the Q value, and this kinetic energy that's dissipated, it has to be greater than zero, right? Because I have to have energy for the Q value, and I have to have energy for the particles to move. So this is something that's important. Actually, the Q value calculators will calculate your threshold energies for you. And for the laboratory frame, as shown here, we just get the threshold energy is greater than or equal to the negative of the Q value times the sum of the projectile and target mass divided by the target mass. And this is all in MeV. So this is an equation that you'll be asked to manipulate. What's the threshold energy for a given reaction? And consider, and we go through this reaction. Imagine I have an alpha particle hitting nitrogen 14, a proton comes out in oxygen 17. Find the threshold energy. Well, we get the mass excesses that are shown here. The kinetic energy is minus the Q value times 4 plus 14 divided by 14, 1.5 MeV. Okay, so that just means that's just the threshold energy. If I don't get 1.5 MeV on my alpha particle, there's no way this reaction is going to occur because it won't provide enough energy for the particles to move afterwards and the Q value of the reaction. Now, this isn't the only thing that's preventing the reaction from occurring. This is just the energetics, but what I actually have to do is if I have an alpha particle and nitrogen 14, I have to get their nuclei close together. And that means overcoming the Coulomb barrier, the repulsion of the charges that +2 and the +7 have for each other. So we use the Coulomb barrier calculation. We did this with alpha decay. I put in one particle, two particles, the A's of the particles, and I get this, and I say, okay, this is the energy of the Coulomb barrier. So this is the energy for just the threshold to occur. But even if I use this energy, I'm not going to get anything to happen because the particles won't get close enough together. So I still have to dump in more energy to overcome the particles, the particle repulsion. And then, by the way, this is a laboratory frame calculation. I'm not including anything moving. So I got to consider the kinetic energy being carried off by the projectile. So I take this value, and if you remember, it's target plus projectile divided by target, and I get 4.3 MeV needed for this reaction to occur. So, and it's not necessarily that the Coulomb barrier is always going to be greater than the threshold energy, but you need to go through, you need to do all these calculations before you would say what energy should we put from the accelerator onto a target. Okay, any questions there?
Yeah, I just wanted to reiterate what you're saying. We have to, when we're like setting the energy that we need, you want to take into account the threshold of energy and also the Coulomb barrier.
Well, yeah, I mean, what you want to do, you want to look at all of them, right? And then you have to pick the highest one,
Oh, I see. So they don't
right?
like add together, but like you want to like
Exactly, right?
okay.
Because what it is, the Coulomb barrier, let's say the threshold energy, that's just says, okay, that's just the minimum energy that accounts for the Q value and the fact that the particles are going to be moving, right? So the
Mm.
kinetic energy of the particles and the Q value for that reaction. But the Coulomb barriers says, okay, not only do those, okay, that's great, that energy is good, but I actually have to get these particles to touch each other.
Right.
And in order for them to touch each other, they have to overcome the Coulomb barrier. The Coulomb barrier doesn't care about the threshold energy, right? It it
Mhm.
it it if you can get the particles to touch each other and then to the nuclei to fuse together, just touch and start fusing together, the energetics at that point will kind of take care of themselves. It could be that now, if let's say if you could overcome the Coulomb barrier, but it's still below the threshold energy, what it'll tell you is that I can make a reaction, but that product isn't going to be seen. There might be other products.
Okay, thank you.
Okay. Right. So now one thing I want to talk about is cross-section values and limits. We talked about cross sections. Let's say fission. We talked about that a barn is based upon the cross section or target that's presented by a nucleus, which is 10 to the minus 24 centimeters squared in area. It's really a probability. But if I look at data on the chart of the nuclides, I can find cross sections that are, I find a lot of cross sections that are much smaller than a barn, but I can find some that are many times a barn. There's a xenon isotope that has a half-life of a cross section that's 1,000,000 barns. Well, that doesn't mean that the nucleus is physically 1,000,000 times larger by just changing a neutron. That doesn't make any sense. It's this equation that we really use for determining what that cross section is. And this is, it's the wave nature caused by the upper limit of the reaction cross section included the Broglie wavelengths. Okay. And where this really comes into play is, okay, here's some more of this system. And these are just the angular momentums that I need to consider. And the cross section is based upon the summation of all the angular momentum potential cross sections. Nuclear reactions can be several orders of magnitude larger than the nuclear geometrical cross section, and this is particularly true for slow neutrons. What I want to show is, okay, if everything is going fast, and here's, let's say if particles, charged particles, or neutrons, this is for neutrons here, this is for charged particles. As everything starts going fast, the wavelengths of those particles get smaller, 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 and their contribution to the total cross section starts to disappear. So they start to converge, and they get kind of close to the geometric cross section. So high energy. So this is when we talk about that example. Well, if I increase the energy of the oxygen 18, why is my cross section going down for that reaction? Because I'm making the compound nucleus and then I'm boiling off those extra neutrons. The de Broglie wavelength doesn't matter that much over at these energies, right? That we're talking, the energies that we were talking about in that cases are on the order of 100 MeV. These thermal neutrons, they really start to demonstrate this, these angular momenta. And your cross section, this is what the equation looks like. And you can see that if there's any sort of contribution from the angular momenta of the particle at the energy, it can really increase the total cross section of the sample. of the reaction. And this is a pictorial where, let's say this is the physical size of the nucleus. And as these states become relevant and populated, the relative size of what the nucleus looks like increases. So this is, an example of incident beam, the plane of the figure, the particle with the particular L, the angular momentum, are considered to strike within the designated ring. So if the particle has a large overlap, an angular momentum overlap, the cross section increases because where it can overlap is much larger than this center part of the bullseye. I don't expect you to we're not going to do any equations with this, but it is just the reason. Why do we see it at lower energies? And the answer is, well, there's the quantum mechanical angular momentum interaction of the condition of the target and the particle interfacing with that target are suitable to increase these cross sections. Because it doesn't happen with every, these thermal neutrons are good for certain isotopes because of the condition of that isotope allows this overlap to occur. Doesn't occur with every system. Okay, so any questions at that point?
No, I'm all good. Thank you.
Okay, good. Yeah. So the way one actually goes about and says, okay, what are some of the cross sections? Well, here's a way of measuring cross sections. Okay, there we go. There. Okay. Now I feel better. Now I can see that. So, measuring cross sections, what one does is look up excitation functions. And you can see you could do an experiment where I take, so here's protons on copper 63. And what I do is I increase the energy of the proton. I do a measurement and I look at what the products are. I look at what isotopes are produced from these reactions. And that tells me what the reaction is, right? So if I have copper 63 on, I'm going to get out my chart of the nuclides. If I have a proton on copper 63, the product of that is copper 63 plus the proton is zinc 64. And then if a neutron comes out, it's zinc 63. Right, so this would be that reaction. So you can measure zinc 63 by looking at, it has some gamma lines. So you could take a foil of copper and irradiate it with a proton at a certain energy, and then look at the gamma lines for zinc 63 and calculate how much is made as a function of energy, calculate the cross section from that, and get this line. So you could also do a proton with, right, so zinc 64, 2 neutrons out, so that'd be zinc 62, right? And as we see, as this decreases, this increases because it's kicking out 2, it has more energy. This is just boiling off 1 nucleon. This is boiling off 2 nucleons. This also boils off a proton. We increase the energy more. This boils off 3 nucleons, right? So I hit it with a proton. So that makes the zinc 64. A proton comes out, that makes copper 63, and 2 more neutrons, 62, 61 copper. So you could take a foil, irradiate the foils at different energies, and then do gamma spectroscopy. And then you can get these excitation functions. And here's an example of an excitation function. Oh, I need to label this better. because this isn't necessarily yeah, this is for making oh, yeah, this is for making element 117, and these cross sections are in picobarns. So I'm gonna have to, but I just want to give you the examples that you can see these excitation functions. So some of them are, this is a 3n, 4n, 5n. So this is the example of what we were talking about for the Rutherfordium. This boils off 3 neutrons. As I keep increasing the energy, it boils off 4 neutrons. If I keep increasing the energy, it boils off 5 neutrons. If I kept increasing it, you'd hit something with 6 neutrons. And the cross section would keep going down, because you might get something that's so energetic that keeping it together in the first place is hard to do. Okay. Here's some more reactions, more cross sections, more excitation functions. This is the specific reactions. Antimony, hit it with an alpha particle, 3 neutrons come out, make iodine 124. Natural zirconium here with a proton, X neutron comes out, make niobium 96. And this is all experimental data, right? If you're doing this, the proton incident energy, the alpha particle incident energy, this is what you actually get from the accelerator onto the target. So you don't have to do any sort of center of mass laboratory frame corrections. This is the center of mass. Excuse me, this is the laboratory frame. The calculations, a lot of times calculations are going to be center of mass, but they'll tell you if you need to consider, sorry, there we go. If you need to consider these center of mass or as laboratory frames, the literature will tell you. Most of the time, the literature, you're going to see this as a laboratory frame. Okay, that ends the first part. I don't know if there's any questions at this point.
No, I think I'm tracking.
Okay, good. Yeah. This is just a reiteration. You get this, this is what we saw earlier. There's this trend, 1 over frequency law governs most neutron cross sections. They tend to increase as the energy increases. This, I'm just showing a trend here. There are obviously these peaks here. This is log, so these resonances can be pretty high. But generally speaking, the higher the energy, the lower the cross section. There's different types of reactions. High energy reactions where you can fragment a lot of, things come off. This is one application of this is spallation neutron source. They have this at Oak Ridge where they make neutrons, lots of neutrons. You can make 20 or 30 neutrons from a reaction by hitting something like tungsten with high energy protons. And you can fragment, you can fragment the nucleus with the liberation of lots of neutrons, because each one of those neutrons are basically taking away 10 MeV. So if you have very high energy protons, hundreds of MeV, you can generate a lot of neutrons. And then this is more high energy reactions. This is kind of a schematic with a particle hitting the impact barrier. And it talks about what's, this relates to what are the actions, the interactions with it, which are occurring in the nucleus. And how does that relate to the products that come out, the excitation of the nucleus? There's ways of evaluating the heavy ion reactions based upon the radius of the particles that need to interact, target and the projectile. There's different types of reactions, inelastic scattering reactions, transfer reactions. So inelastic scattering is just you're taking some of the kinetic energy of your target and transferring some of that kinetic energy to the nucleus. So you may not have any particles exchange, it just might be energetics, but it could still remove some particles from the target. These are transfer reactions where maybe I have something like oxygen 18 hitting a compound nucleus, and it doesn't completely fuse together. Maybe an alpha particle from the oxygen 18 gets transferred to the target. So it's stripping and picking up reactions. And then there's this is kind of the schematic of the reactions that can occur, these peripheral reactions. This is the fusion. These grazing reactions can they can have lots of kinetic energy change. They can also have some nucleon change. And this is where we also see this 5 to 10 MeV de-excitation for neutron evaporation. So a particle comes in, forms this nucleus. It has lots of energy. One of the ways it can de-excite, it can get rid of 5 to 10 MeV by just boiling off a neutron. And this is just some detail. And then there was this figure that I like from nuclear and radiochemistry where this particle's happy because it just got scattered, where these particles start changing because of their interactions. Another particle, we've talked about charged particles, talked about neutrons. Photons can also drive nuclear reactions. And this is just, this is just to be complete. So here's an example of gold reaction with photons, making some gold isotopes. This could actually be used, and it is used in gold mining. Imagine you have some ore and you want to know if there's gold in the ore. You can have that ore pass through a photon source at these energies, at these energy ranges. So let's say you have something that's giving off photons between 10 and 20 MeV, and it hits gold, you know, because you're gold mining, and it knocks off 1 neutron, 2 neutrons, or 3 neutrons of that gold. Most of the time, it looks like it's going to be a 2 neutron. So gold 197 is a stable isotope. Gold 195 is the 2N reaction. And that has that is a gamma ray at about 98 keV. So imagine if you had some ore and you hit it with these photons and it started to, the intensity of the 98 keV line got really high. That would tell you that there's lots of gold, or relatively high amount of gold in that ore. You can also do photofission. So photon comes in and fissions some uranium. The neutrons come out. They use this for detecting neutrons. Actually, detecting uranium in samples. All right. Any questions up to this point? All right. So what? See, what I'm going to demonstrate or talk about here is nucleosynthesis. How we use some of these reactions to describe how all the elements are made in stars. So this is a timeline from the Big Bang where protons, neutrons are made. That makes them really simple. You know, we've made a couple elements on the periodic table. These clouds get together, they start to fuse. You can fuse elements up to iron. That fusion process is also producing neutrons. And then those neutrons can be made, can be involved in neutron capture of isotopes all the way up to bismuth. And then when stars go into nova, before they collide, the neutron fluxes get massive, and then you can make something like the actinides. That's the short scheme of what we'll describe here. So basically, we need to be able to say, okay, how do we make everything in the yellow? And by the way, everything that's this black line here, those are all the stable isotopes, and I'm including uranium-238 out over here, so thorium-232 out over here. And we're going to see that, yeah, making everything up to here makes sense, and we'll talk about how we make some of the stuff off the line. But getting out to here, it's a little bit trickier. Okay, so the Big Bang happened around, 10 to the 10th years ago. High temperatures, cooling, lots of hydrogen, some helium, 3 neutrons. Any neutron that didn't find a home in a nucleus decays. It has a half-life. They have a half-life of about 18 minutes. So we got these elements on over here. How do we get everything else? Well, these coalescence of the hydrogen and the helium into clouds. They continue to coalesce. They form stars. Temperatures increase. So fusion can start to occur. If you remember, we talked about the binding energy curve. I can make all these reactions to give off energy. Particularly, let's say this reaction or this reaction, things that make helium very energetic. So if I have this reaction, I make helium, I've got this extra neutron. This is kind of a schematic of some of the reactions that can occur. I can make lithium-7, beryllium-7. So initial nucleosynthesis lasted about 30 minutes. We talked about that in the previous slide. These stars start making other elements. This is our binding energy curve, right? As long as I'm fusing elements, isotopes on this side, I can get energy out up until I get to iron. So we can start making a bunch of elements. Now, a bunch of isotopes. One thing I do want to point out, carbon-12 is kind of interesting because if I were to take, carbon-12 is, I've got helium. I should be able to get the beryllium-8, and then beryllium-8 plus another helium will give me the carbon-12. However, beryllium-8 has a half-life of I'm looking it up. It's small, like 10 to the minus 20th seconds. Something along those lines. Beryllium-8 is 7 times 10 to the minus 17 seconds. So you make that nucleus, and the half-life is 10 to the minus 17 seconds. So you would need to have, you basically need to have another helium hit that beryllium in that time frame to make carbon-12. That's too short. What actually happens is something that we're told is never supposed to happen in physics, and that's the three-body reaction. And this, if there's 3 helium nuclei that fuse together instantaneously, you can make carbon-12, and there's a lot of energy with this system. 7.4 MeV above the ground state. So it was proposed based upon this reaction that, well, carbon-12 probably has an energy level that's close to this. So that if this occurs and this isotope is made, that a gamma can take away most of this energy and the isotope won't just fall apart. And Hoyle, called the Hoyle state, because Hoyle was researcher named Hoyle was the one who proposed it. They see this ground state here, and this is a state that, it could kick out an alpha particle, but it can also emit photons to go back to carbon-12. So this state allows carbon-12 to be formed. And it's interesting because it's based upon the three-body problem that we were told should, in physics, we're like, well, that's a low probability reaction. So the isotope that everyone is, always points out as a very important isotope, carbon-12, comes from that, right? So you can there's something called the carbon, nitrogen, oxygen cycle, just shown here, how these elements get built up. And then once you start building up these elements, based upon this figure, we can fuse, stars can get energy by fusing elements all the way up to iron. Okay, so that explains, a good part of the periodic table. But then how do we get above iron? Well, if you remember, let's see, there's neutrons that are produced in some of these reactions. You go back over here, you see that there's neutrons that are produced. So there's a sufficient neutron flux in a star where this S process for slow can occur. And imagine that you have elements and they capture isotopes, they capture a neutron, they make an isotope which is neutron rich, it's beta unstable, it's radioactive. That neutron converts into a proton, it moves up the periodic table. So here's rhodium going all the way, from 45 all the way up to around 60, neodymium. And you could see where it makes all these isotopes on this part of the periodic table, on this part of the chart of the nuclides. And then this isotope would decay to keep building up, and this will go all the way up to bismuth. You get the bismuth 209, you make bismuth 210, that'll beta decay to polonium 210, and polonium 210 has a 140-day half-life, and it alpha decays. So I'm dropping down. It doesn't beta decay anymore. So that's kind of the limitation. All right, now we've got most of the isotopes that we can identify. We've got some of these that I can't reach and some of these that I can't reach. Well, let's figure out how we get those. This is S for slow process. This is R for the rapid process. So the neutron capture timescales are much shorter than the beta decay lifetimes. So what this means is that the neutrons flux is so high that it makes an isotope, and that isotope sees another neutron before it can beta decay. So these are extremely high fluxes. The neutron density is something by the order of 10 to the 28th neutrons per meter cubed. This is around 50 molar. Let's say it's around the same molarity as water. So imagine that the density of neutrons is similar to water density in liquid water. So it's extremely high neutron fluxes. So you can capture something over here and make something over here very rapidly, and then it beta decays up to here. And now all these isotopes that are off the path that are heavy, I can populate them. I can make them through this rapid process. And then there's a P process, proton capture process, photonuclear processes at high Z. P process means both. And now I'm making these isotopes that are light. They're stable, but they're neutron light. So the P process will make these light ones. The R process will make the heavy ones, and the S process will make the ones in the middle. Then, similar to the rapid neutron process, there's a rapid proton capture, which makes some more of these isotopes out on this edge over here. And that's let's say that's where that's a review of how elements are made. It's pretty, again, I wanted to hit some of the high points for the elemental synthesis, R process and S process. Those are the ones that are going to get you most of the isotopes. If you're light, that's going to be the P process. The take homes for this is, be able, let's say, describe some of the reactions that happened here. Be able to do some notations, find threshold energies, difference between low and high energy reactions in terms of cross sections, as shown here. Understand excitation functions. Why do they have that shape that they do? And then what are the S processes? And what's interesting about the carbon-12 production? So a lot of the lecture, some of these details in the reactions, the high energy reactions, I'm not going to necessarily, I put that in there for completeness. I don't expect you to really go into the details of understanding, what are some of the transfer reactions, but just understand things about the compound nucleus and particularly how it relates to reaction energetics. Okay. Any questions?
I don't think I have any questions. Thank you so much.
Okay. All right. Thanks. I'm going to stop the recording and others can hear this so that they can always like to do that. So in case people